In this video number 2, I will speak about basic definitions and terminology. So, a Boolean ring is any ring satisfying x equals x for all x. In other words, where multiplication is idempotent. So, let's first prove that in any Boolean ring, x plus x equals 0. So, you do it like this: x plus x times x plus x equals, by the idempotency of multiplication, equals x plus x. Now, if we open the parentheses, we are going to get xx plus xx plus xx plus xx equals x plus x, but due to idempotency of multiplication, we can delete one x in each of those. And because it is a ring, addition is a group, so I can cancel on both sides, and I simply get xx equals 0. Further, any Boolean ring is commutative. To do so, we try to evaluate, we write down this expression, which of course, again, has to be true because of idempotency of multiplication. Now, let's distribute. Let's use the distributive law. We get this thing. Now, this y can be just y because of the idempotency of multiplication. This x can be simply x. And now I have here x plus y. I can cancel it from the left-hand side. So here I put 0. Here I remove this. And what we get is xy plus yx equals 0, which is actually xy equals minus yx. But from this equation, we conclude that x equals minus x for any x, and therefore xy equals yx, so the ring is commutative. Ring, as you know, has the signature multiplication, addition, 0, and 1. Boolean algebra, as you know, has the signature, and I'm going to use this notation. This is going to be conjunction for, I'm going to use set theoretic operations in order to distinguish it from logical connectives, as we shall see. Conjunction, disjunction, and complementation, I'm going to use prime. Any Boolean ring is a Boolean algebra and vice versa by multiplication is directly conjunction. Disjunction, so A disjunct B is the same as A plus B plus AB in the ring notation. Complementation in the ring is just 1 plus A. And if we want to go from ring to Boolean algebra, A plus B, then plus is symmetric difference, or XOR. So A plus B can be written as AB prime union A prime B. Now, a Boolean function is possibly multivariate, a polynomial function over a Boolean ring. Note that I say polynomial function. I don't say polynomial, because polynomials can have terms of this form. A polynomial is a formal object, but in a polynomial function, because of the idempotency of multiplication, polynomial function in Boolean algebra, we never need to write any exponent. So a univariate polynomial, in other words, a univariate Boolean function, has this general form, where A and B are elements from the Boolean algebra we are talking about. Indeed, to write down a Boolean function, generally speaking, you need to fix your Boolean algebra. Maybe that's time to say that the term Boolean function is very unfortunately used today in completely different meaning. It is used in a meaning that which we shall call simple Boolean function. Simple Boolean function is a Boolean function where all coefficients are either 0 or 1. Simple Boolean function is a BF where all constants appearing in it. So here I'm writing a syntactic definition, but we will soon see how to give semantic definition are either 0 or 1. Now, any Boolean algebra has 0 and 1, and therefore a simple Boolean function makes sense over any Boolean algebra. But as long as your Boolean function is not simple, then it makes sense only in the Boolean algebra from where your constants came from. Boole's normal form or the composition, mistakenly also called, especially in the BDD literature, as Shannon normal form or Shannon's decomposition, is to write a Boolean function of the form ax plus bx prime. Now, several things to notice here. First, you can completely equivalently write here a union instead of sum. This is because this joint union is same as disjoint symmetric difference. If you have two disjoint sets, then their union is the same as their symmetric difference. And here we indeed have two disjoint sets, because here we have x, and here we have the complement of x. By the way, I used juxtaposition for intersection. So that's why these two forms are completely equivalent. This is simply equals this. This form is called algebraic normal form. So in the algebraic normal form, we have this. And to move from, let's say, algebraic normal form to Boole's normal form, that it's very easy. So for one thing, observe that this A is nothing but f evaluated at 1. And this B is nothing but f evaluated at 0. So any univariate Boolean function you can write this way. More generally, you can write a Boolean function in Minterm normal form. So first, a Minterm is of the form capital X to the A. Now, capital X is a tuple of variables, and A is a bit string. So this thing is really a conjunction of x1 to the power of a1. So maybe we write it as a big product. Where the meaning of this this exponentiation, it got nothing to do with exponentiation. It's really just a convenient notation. So x to the 1 equals x, and x to the 0 equals x prime. So if you have three variables x, y, z, then this is a Minterm, and this is a Minterm, and this is a Minterm. So you have 2 to the 3 Minterms. You always have 2 to the n Minterms in n variables. A Minterm is actually a DNF clause, but under the assumptions that all variables appear in it. And this is important. Usually, we use Minterms to make the assumption that all Minterms are disjoint. Indeed, if two Minterms are different, then one variable appears positively in one Minterm, and another variable appears negatively in another Minterm. Therefore, the conjunction is 0. So we can see that two different Minterms, any two different Minterms are disjoint. Now, any Boolean function of multiple variables can be written in Minterm normal form in this way. So here I write big union, but the very same way I could write sum, because we are going to have disjoint union, and as we said above, it's the same asymmetric difference. A runs over all n bit strings if x is a tuple of n variables. So we evaluate the function at all possible zeros and ones, and we multiply by the corresponding minterm. Boole's decomposition is a special case where we have only one variable. So we evaluate f on 0 and then 1, and we multiply by the corresponding minterm, and we get a representation of the function. So as a conclusion, any Boolean function is fully determined by its values on 0, 1. A simple Boolean function will always return 0 or 1 as long as its input is 0 and 1. But a general Boolean function, you can plug in 0 and 1, but what you are going to get is not necessarily 0 or 1. So for example, if we have a power set algebra, of course, every power set is a Boolean algebra with respect to the standard set theoretic operations. So if you have fx takes, let's say, the power set of the natural numbers, so we take a constant set that contains the numbers 1, 2, intersected with x. That's a Boolean function. 1 in this Boolean algebra is going to be the whole set, the full set, all natural numbers. So f1 is going to be this set.